In this video, I'll be discussing a situation where we have two spherical tanks open to the atmosphere that are connected along the bottom with a pipe, and the second tank also drains out through pipe 2, and that is also at atmospheric pressure. Both tanks have inlet flows, and as you can see in the situation that I have drawn out, it's exactly as described, and we have some given measurements of respective radius, heights, and areas for each tank and pipe. So the purpose of this video is to first derive steady state equations needed to calculate initial flow rates into the tanks, and then to derive differential equations to solve for the time variation for the fluid height in both tanks. So the first thing we want to do is derive steady state equations to calculate the initial flow rates. If we know that the flow rate is equal to the cross-sectional area of the pipe times the velocity of the fluid moving through the pipe, then we really just need to derive an equation for velocity, since we know the cross-sectional area of the pipe, A2 for the one in between the tanks, and or A12 for the one in between the tanks, and A2 for the one that's the outlet of tank 2. So to write this out, we have the flow rate of the pipe between tanks 1 and 2 is equal to the cross-sectional area of that pipe times the velocity of the liquid moving through it. And the same for the outlet pipe. And both of those cross-sectional areas are 0.2 meters squared. So we can say that it's equal to this for both. And then we just need to derive an equation for those velocities. So we can find velocity using Bernoulli's equation, which is the difference of the pressure over the density plus the gravity times position plus kinetic energy, if we assume that there's no non-flow work or frictional heating. So, and it's the change in that. So write that out. So for the first tank, we can assume that the initial velocity is equal to 0 because the cross-sectional area is so big in comparison to the cross-sectional area of the pipe. So for the first tank, we have final pressure minus initial pressure over density. And then since pressure is equal to rho GH, we can simplify this. And then for the second tank, we can do the same thing and assume that initial velocity is equal to 0 because of the cross-sectional area difference. And we also know that the change in pressure is equal to 0 for the second tank because the pressure is the same at points 1 and 2. So this all cancels since the change in pressure will be equal to 0 since they're equal. And we can rearrange that for velocity. And we can rearrange this one for velocity. And there we go. So the velocity of the liquid moving through the pipe between the two tanks is equal to the square root of 2 times the gravity times the difference in height. And the velocity of the liquid moving through the second pipe, the outlet pipe, is equal to the square root of 2 times gravity times the final height. So we can just go ahead and plug that back into our initial flow rate equations, and then we have our official flow rate equations. Okay, so next we need to derive the differential equations to solve for the time variation of the fluid height in both tanks. So the change in volume with respect to time, which is going to be the flow rate going in minus the flow rate going out. So we can say that dv over dt is equal to the flow rate going in minus the flow rate going out. And if we want to apply this to both tanks, we can take it over here and say that the change in volume of tank 1 with respect to time is equal to the initial flow rate in tank 1 minus the or the flow rate into tank 1 minus the flow rate out of tank 1. And then for the change in volume of tank 2, you can say the same thing. So I'll take it to the next page so that it's cleaner. So we have, I'm going to rewrite something. So let's start with the first one. We have our equation for the flow rate out. So we can just go ahead and put that in and keep our input flow rate, which is the input into the tank, as keep it as Qn1. And since we're doing the absolute value in that square root, we can just keep it that way, have h1 minus h2, but then account for the possible sign difference outside of the square root, which is what I'm about to write here. So whatever the sign is of h1 minus h2 will go here, times 0.2, which is that cross-sectional area. Okay. And then for the second one, you can do the same thing. And for the output flow rate of the second tank, we have to include the flow rate from the first tank from that pipe connecting and the output pipe. So now knowing that the change in volume with respect to time is equal to the cross-sectional area of the tank multiplied by the change in height with respect to time, we can find and derive two expressions for the change in height with respect to time, which is the target. So we want to find dH over dt. So for the first tank, it'll be this. And that's all divided by the cross-sectional area of the tank. And then for the second one, we'll have essentially the same thing. Okay. And then to find the cross-sectional area in terms of height, we have to do some geometry. So if we draw it out, and say that that's the center of the circle. It's kind of a wonky circle, but this would be the radius. This would also be the radius. And this is kind of similar to finding that cross-sectional area from the log on water problem. So break it into triangles. So if we take this right triangle with the long side as the half of the water level, draw it out here. We just call this RT. Then we know that the cross-sectional area of the tank is equal to pi RT squared. And using Pythagorean theorem, we can say that r squared is equal to r of t squared plus h of t minus r squared. And then we can rearrange that to find r of t. And then we can plug that back into that cross-sectional area of the tank equation. So basically just multiply radius squared minus the height minus radius squared times pi. And that gives us our cross-sectional area. Okay, so now we can plug this expression for the cross-sectional area of the tank back into the differential equations, and that is our target. So that's what we need. So the change in height with respect to time for tank 1 is going to be equal to the input flow of tank 1 minus that sine of the height difference times the cross-sectional area of the pipe connecting the two tanks square root of 2 times gravity times the height difference and divided by the cross-sectional area of the tank. And then the change in height of the second tank with respect to time is equal to the input flow of tank 2 plus that sine difference times the cross-sectional area of tank 2 times 2 times gravity times the height difference minus the cross-sectional area, the square root of 2 times gravity times the final height over the cross-sectional area of the tank. Okay, so there we have it. Thank you so much for watching this video.